Hello there, and in this video we're going to talk about a statistical method that is used to answer a question that a lot of us may ask throughout our lives. That is there an association between two or more variables? Or are those variables independent of one another? So in this video we're going to consider a sample set of data between males and females versus people who don't smoke and people that do. So one may ask, is there an association between the gender and the smoking habits, or are they independent quantities of one another? So another way of sort of thinking about this question is in the following. Is there a significant variation between the categories? And the key word here is, of course, variation, and I'll say why. Because remember that variation is sometimes associated to a chi-square random variable. So recall that the chi-square distribution was able to allow us to get a confidence interval for the variance of a population. Also, there's definitely some connection between these two concepts, which motivates us to possibly use chi-square for this test as well. And this is sometimes referred to as a chi-square test for independence or association. So that's what this test is commonly referred to as. All right, so let's lay down some concepts before we sort of build our theory. So if there is a large variation amongst our categories, then we will at least have some idea that there may be some dependency among X and Y. And some people say there is an association among X and Y. And if there is a low or small variation amongst the rows and columns, then we may think that there's some independent of one another, or there is a disassociation. And some people use the word significance in these concepts. Because some people may refer to the butterfly effect, that pretty much everything affects one another. But we're going to be focused on is there a significant dependence or a significant effect that one has on the other. All right, so since we're going to perform a hypothesis test, we need to sort of declare a null and alternative hypothesis. So the null hypothesis that we're going to do is that X and Y are independent of one another. So if that is going to be our null hypothesis, then a fair alternative is that X and Y are not independent on one another. We're not going to say that our alternative is that X and Y are dependent on one another, because if we say that, then that means we have to prove that there's some functional relationship or some causational effect between the two. So we're just not going to focus on proving that they are dependent. Rather, we're just going to prove that they are not totally independent of one another, which is why I phrase it this way. So since we're going to try and show that X and Y are not independent, then that means we desire only a large variation for proof of this, or I guess you could call it proof for this alternative hypothesis. So let's look at our normal distribution to sort of get an idea of how we're going to conduct our hypothesis test. So this is going to be X, and this is going to be our chi-square of X axis. So here's our chi-square distribution. So we are only going to sort of reject the null hypothesis if we can get some values that are in the upper end of the spectrum, not necessarily in the lower end, because we want large variation here. So if that is the case, and that means there exists some value here. I'm going to call it a critical value because that's what we usually call it. So there's going to be only one critical value that's sort of going to separate the values that we accept and the values that we don't accept. So that means everything to the left of this distribution is going to be our region of confidence. So this is what sometimes we call a one-tail test. Okay, so since that's a one-tail test, then that means how do we find this critical value? Well, that means the integral from 0 to this number of interest under the chi-square distribution with respect to x must be equal to c. So we can use Excel or integrals solutions to sort of find out what this critical value is. So in Excel, chi-square crits is going to be equal to CHISQ.IMV of c comma v, or nu. So here, the degrees of freedom for contingency table, remember, is the number of rows minus 1 multiplied by the number of columns minus 1. So this is always going to be true. So since our degrees of freedom is equal to the number of rows minus 1, because we have two genders of interest here, and then two columns that we have, because we either have smoking or non-smoking, the degrees of freedom for our case is going to be 1. And if we choose a level of confidence to be equal to something, let's say 0.98, so we're going to build a sort of 98% confidence interval rather. So from these two things, you're going to find out that the critical value associated to this type of test is going to be approximately equal to 5.41189. Okay, with that being said, that means we're ready to sort of build a test statistic to sort of test against this critical value. For the remainder of this, I'm not really going to derive where these formulas come from, but I'll sort of explain what they represent. So step 1 for this hypothesis test, we're going to calculate what we call the expected frequencies. So let me sort of explain what exactly an expected frequency represents. So let's go back to our data values, and I'm going to sort of abbreviate it in this table. So 127, 523, 82, and 672. So if this, and this is sometimes what we call the observed frequencies. So of course this is going to be the male, female, smoking, and non-smoking. If you look here, we see that 82 people, 82 females smoke, and 127 males smoke. So if you just look at this table, you may be tempted to say, oh, more males smoke than females. Well, that's not necessarily true, because we might have surveyed less females than that of males. So this may be, sort of misleading based on, how many people we actually had in our sample. So what the expected frequencies does is sort of pretty much normalize the playing field based on pretty much the total amount of people surveyed in our whole entire spectrum. So the expected frequencies, I'm going to denote it here. I'm going to write it as EJK is going to be equal to the sum of row J times the sum of column K, all divided by our total sample size N. Okay, so that means we need to consider the sums. So recall that we had 650 males surveyed, and we had 754 people surveyed that were females. We had 209 people surveyed that smoke, and we had 1,195 people that didn't smoke, with a grand total of 1,404 people that were surveyed across the entire spectrum. So we're going to refer to these cells as 1, 1, row 1, column 1, row 1, column 2, row 2, comma 1, and row 2, column 2. So 1, 1, 1, 2, 2, 1, and 2, 2. All right, so we're going to calculate our expected frequencies here. So the expected frequencies, so I'm going to abbreviate this by EJK. So for this first cell here, so 1, 1, this is going to be equal to the sum of row 1, which is going to be 650, sum of column 1, which is going to be 209, divided by the total sample size. And if you calculate this out, then you should get something about equal to 96.76. So if we look at row 1, column 2, so row 1's total is going to be 650 again, but column 2 is going to be 1195, all divided by a sample size is going to be 1404. Once you calculate that, it's going to give about 553.24. All right, and you're going to do this for all your cells, so you're going to get 96.76, 500.4 again, 112.4, and finally 641.76. So these are your expected frequencies for each of these cells. So let's go back to our observed frequencies again, which I'm going to abbreviate by OJK. So what were those equal to? So the observes was equal to 127, 523, 82, and 672. Okay, great. So step 2 is the test statistic. So the test statistic for a chi-square test for association is going to be equal to the sum of the minus the observed frequencies, the quantity squared, divided by the expected frequencies, and we're going to add all those things up, and that's going to be our chi-square stat value. All right, so exactly how are we going to calculate this? So let's go back up here. So our expected frequency for row 1, column 1 is 96.76, and our observed is going to be 127. So we're going to subtract these two numbers. So 96.76 minus 127, and divide by the expected value, which is 96.76. Plus, and then we're going to move across the entire table. So 553.24 and 523 are the numbers we're going to subtract. So 553.24 minus 3 the squared, all divided by 554. And we're going to do this for all values in that whole entire table. So once we go through that process, and this is easily done in Excel, you're going to get a stat value of approximately, let's see, what is this going to be? That's going to be about, let's see, that's going to be equal to 20. So that's going to be our chi-square stat value. All right, so what can we do with this number? So recall our chi-square critical value was equal to 5.1. So if we look at our picture here, so here's our chi-square distribution. So our chi-square crit value is, and that pretty much, and what we have here is we have a chi-square stat value here, so 0.68. So we want a high variation amongst all the rows and columns, and what we have here is definitely greater than our critical value. So that means what? So since the chi-square stat value, or our test statistic, is larger than our chi, then we're going to reject the null hypothesis, which we're going to reject the claim that x and y are independent. So what does that mean in terms of this test? And that means we have evidence to support that there is an association or relationship. That is, there is a possible relationship between the gender and the smoking habits. Now, it doesn't necessarily mean that there is a strong association. It doesn't necessarily mean there's a weak or moderate association. This test doesn't really justify that. There are other tests to sort of measure the strength of an association. But this test pretty much tells you that, there's a significant difference amongst the rows and columns. So, there's a possible association amongst these variables. And that's how you can pretty much conduct a chi-square test for the association or independence between two variables if you have the contingency table for the data for that study.